for AP Chemistry is the concept of equilibrium. So the main idea behind equilibrium is to remember that any bond, any intermolecular force, any reaction that can be performed or that can exist can be undone. And so this forward and reverse reaction will form a dynamic equilibrium. So the main concepts here is first and foremost being able to write an equilibrium expression and understand the concept of equilibrium. And then after that, all these smaller pieces that fit in under that. Le Chatelier's principle, reaction quotients, multi-step processes, the solubility product constant. These last, the common ion effect, the last three, although they do fit into equilibrium, probably won't appear on the test because they are more focused on the acid and base unit, which is not included. So when we talk about equilibrium, that's obviously the biggest part of this idea. There are several pieces to equilibrium. First is just being able to write an equilibrium expression, both in terms of concentrations and pressures. And then we, of course, have a relationship between those two. Another big concept was being able to use the ICE tables to solve calculations, being able to solve for the reaction quotient and interpret the reaction quotient, applying Le Chatelier's principle, and understanding solubility constants. So when writing an equilibrium expression, we have our balanced chemical equation, and the coefficients in that equation just become the exponents in our equilibrium expression. It's written as the concentration of products over the concentration of reactants. So each product we have gets written in square brackets along with an exponent that's given by its coefficient in the chemical reaction. It's always products over reactants. We always have to use these square brackets to show concentration, and we only need the aqueous and gas phases because these are the only two places where concentration makes sense. You can have concentrated orange juice because orange juice is a mixture of, orange juice and water, and you can have more or less orange juice relative to your water. You can't have concentrated brick or concentrated oranges or concentrated water. Those substances just are, right? You can't compress them. You can't squeeze more atoms into them. Aqueous phases can change concentration because you can dissolve more or less particles. Gases can change concentration because you can compress them. If the equilibrium constant is greater than 1, that would indicate to us that equilibrium favors the forward direction, that there are more products than reactants. For this number to be bigger than 1, the numerator must be bigger than the denominator. If the equilibrium constant is less than 1, then the reverse reaction is favored. There are more reactants than products. For this number to be a fraction, to be less than 1, the denominator must be bigger. If it equals 1 exactly, then our system is at equilibrium. There's an equal balance between both reactants and products. The concentration of each would be perfectly equal. Remember that we can write the equilibrium expression in terms of concentrations or in terms of pressure if we're dealing with gases, and this equation allows you to convert between the two. Delta N here is the difference in the number of moles of gas between the products and the reactants. We did several examples using ICE tables. If you weren't super comfortable with those, go back and try a couple again or try a couple new ones. The whole point behind the ICE table is being able to use the stoichiometric relationships of the reactants and the products to figure out the equilibrium concentrations after the reaction is complete. So there are a couple strategies that you can use. Typically, you'll assume that the reaction is occurring in the forward direction, that the reactants are decreasing by some amount x, the products are increasing by some amount depending on the stoichiometric relationship, depending on their mole ratio in the chemical equation. And you'll get expressions for the equilibrium concentration, the initial number minus x or minus 2x or so on. And so typically you'll plug those equilibrium expressions into your equation for the equilibrium constant, and you'll be solving for x. And you can do that either by completing the square or by using the quadratic equation. Sometimes you can make your life a little easier, and when you think it's safe to assume that that x is going to be very small, I'll correct that, that should be x, that when x is going to be very small compared to the initial concentration, if it's going to be less than 5% of the concentration, then you can assume that any subtraction or addition of it would be negligible, would just be a rounding error. So, for example, if your initial concentration was 0.5 and your equilibrium expression is 0.5 minus x, but you're pretty sure that x is going to be a very, very small number, you can just set that equal to about 0.5 and solve. Just be sure if you do this, if you take that shortcut, once you've solved for x, go back and check that it is in fact less than 5%. If it's greater than that, then that assumption is not safe to make, and you will have to go back and use the quadratic equation. We can also use reaction quotients to predict what a system is going to do. So the reaction quotient is just like the equilibrium constant as far as its equation goes, but you can plug any concentration into the reaction quotient. It doesn't have to be the equilibrium concentrations. And then you'll compare the number you get to K. So if you plugged in your concentrations and your Q came out too small, it was less than K, then your reaction needs to make more product. It needs to move forward so that Q gets bigger. If Q is greater than K, then your reaction has too much product. Q needs to get smaller, so you need to consume some product to make some reactant so that as you plug in concentrations, Q decreases until it reaches K, and so your reaction will move in the reverse direction. If Q perfectly equals K, your reaction is already at equilibrium. All right. Finally, we talked about Le Chatelier's principle, which said that anything that disrupts the equilibrium to a system will be counteracted by the system. The system will act to minimize any disruption or change. So if you add more reactant to a system, the system will shift to the right, it'll shift towards the products, it'll use up that added reactant to make more product to restore its equilibrium balance and its equilibrium ratios. So you can disturb the equilibrium either by changing concentration, by changing volume or pressure if you've got gases, or by changing temperature. Changing temperature actually changes the equilibrium constant as a whole. Changing pressure will cause the system, if you increase pressure, the system will want to minimize that. It will want to undo your change. It will want to shift to the side with fewer moles of gas so that it can decrease its pressure. The couple of exceptions were if you increased the pressure by adding a noble gas or an inert gas, that has no change because you haven't actually changed the equilibrium ratio between your reactant and product gases. Finally, remember that adding a catalyst will allow the system to reach equilibrium faster. It will increase the rate, but it will not change the equilibrium composition. Finally, we had special cases of equilibrium when we were dealing with solutions and solubility. So you can write an equilibrium constant, KSP, called the solubility product constant, for dissolution equations, and it'll just look, you will only be including the products, because remember the equilibrium expression doesn't include solids, only aqueous phases. When you're doing this, one other important thing to keep in mind is the common ion effect, just the idea that if you add a common ion to a solution, the solubility of your salt is going to decrease because you would have added product, your system's going to shift back towards the reactant. It's going to make more of the solid, it's going to form a precipitate. You can also use Q to predict whether a precipitate will form. Again, if Q is greater than K, there's too much product, you're going to shift towards the reactants, which happen to be solids. This also came up in pH and solubility, but luckily that is also not included this year. All right, those were all of our big ideas. Hopefully it was useful to sort of hear the ideas organized in a different way and arranged in a different way. Hopefully it was useful to hear some of the main ideas just brought up again to kind of refresh them in your mind, remind you what you felt really confident about, what you might want to go back on. Continue working through practice problems, and feel free to email me if you come across any that you have questions on or want further explained.